Hello, everybody. So tonight starts module 3. 16-week courses really stretch out. Our 8-week courses are up in module 5 now. This will probably be one of the last 16-week ones. Everything, which when everything is consistent, it's a little bit better. Y'all have probably noticed that all the 8-week courses are, our rhythm is kind of thrown off in the 16-week course because we're in the habit of doing a lot more in a very short period of time. But starting into week 3, and a very big deal for Java, we're going to look at object-oriented programming tonight, and Thursday night, and next Tuesday, and following Thursday. And well, we've already been looking at object-oriented programming because Java only does object-oriented programming. So we're going to dig into the finer details, start trying to make sense of that, which actually is kind of nice, because with object-oriented programming, we kind of get to think like a human again. Because first, when we're learning to program, we have to adjust everything we do and so that it goes into the machine. And I always like to start off with a couple pictures here. For some reason, his isn't joining. Hopefully it won't take too long. Pretty sure you've seen me draw this picture before. So I always like to start off with these pictures when we get to the object-oriented programming section. One from another subject altogether. You probably don't regularly tie into any computer classes, right? Just come over to biology and look at something in biology. So I think everybody has to have at least a biology class to graduate high school, right? And it's a very popular science class to take because one of Ivy Tech's big thing is the medical stuff, right? The nursing students, the medical coding, the radiologists, the lab technicians, all the medical school. That's a really big thing at Ivy Tech. So biology is, they have to take biology, which means biology is going to run pretty much every semester at every Ivy Tech campus. So that's an easy one to fill in that science grade, as opposed to waiting for 3 years for the next time there's enough people to run a physics 2 class. It's one that, so a lot of people have seen it, but the thing I want to look at there is how we categorize stuff. You may have seen it before, the tree of life. I'm going to write it, go top down. And in biology class, you would have had up at the top, we have this just general catch-all category of life forms. All life's obviously a life form. But then that breaks down into some more specific things. From biology, we'd have the archaea, bacteria, and eukarya. 3 different branches that are a little bit more specific. They're still life forms, but there's some slight differences between them. And then those get more categorization as we go down, like a particular type of bacteria might be E. coli. I don't know very many of them off the top of my head, and very few bacteria have even names that we can spell out. Staphylococcus. I'm not even sure how to say it. Strep throat, yeah. Y'all have probably heard the word. Did you say Streptococcus? Streptococcus, yes. Y'all have probably heard that's at least, that way I can put at least 2 branches. So they're still both bacteria, but a little bit more specific, those differences between them. The standard test in a biology lab, one of those is going to turn pink, and one's going to turn purple for that, the simple quick lab that most biology students see. Yeah, one of them's a rod and one of them's a circle. So they have a different shape. Eukarya, I know a few more of those, right? We might have fish are one type of eukarya, and plants and mammals, things that they have some similarities, but they're more specific types in that category. Then you can keep going down, like from mammal and accentuate the arrows here. A couple types of mammals might be elephants and canines. The canine, we can get more specific even here. So maybe a red wolf. I'm probably skipping some steps here, but just the general picture is all we're looking for here. Or versus the dog subcategory of canine, where we have more specific things like a beagle or a black lab or a chihuahua. And that big tree of life. I'm guessing everybody's at least slightly familiar with that, right? The connections between all the life forms on Earth and how we categorize things. And that's the big issue, right, for tonight, why I'm bringing this up. This is how humans naturally categorize things. We start with the most general form of it and then start adding details with each layer. Whether we draw the tree going downward or upward, it doesn't matter. We start with the most general, which is the root. And since we're in a computer class, I put the root on top. Biology people usually put the root on bottom because they're thinking about like trees, like an actual tree. But in computers, we draw our trees go downward. But we start with the most general and then add details at each level and get more and more specific. And that's just the natural way that humans categorize things. When we take it beyond biology, talk about different types of construction, different buildings, our categorization for retail versus household, right? Residential, right? Y'all probably all got a picture in your mind when I said retail and residential, and a general details that separates those two. Even though we've all seen former houses that were turned into stores, or seen former stores that were turned into living spaces, right? That categorization of adding details, and those are all just types of buildings. So it's the way humans naturally categorize things. And with object-oriented programming, we get to categorize our data that way. We categorize our data in the way that's natural for humans to do it. And a few things that I want to point out on this picture that will apply to what we're looking at. As long with those connections, we're getting more specific as we go down. So things are inheriting the properties of the level above them. Right? There's just those most basic properties that it means to be a life form. So a few descriptions coming on over the years. The best one I ever saw was actually released by SDEV, the Search for Extraterrestrial Intelligence. In the early 80s, one of the scientists working there, his grandma stopped by to visit, because they were in Florida, a nice place. That's where people came on vacation. His grandma stopped by to visit, see what he was doing. She was all proud of him, having recently graduated, and his grandma was talking to the different scientists. They were talking about some of the troubles they would find. So the lady's just like, no, it's life. There's not going to be trouble finding it. And they're like, what do you mean? And she's like, life's squishy. And basically, you'll recognize it when you see it, right? We can look at something and tell whether it's alive or not. That's one of the best descriptions I've ever heard, and something that he actually released. So it made it into the official science documentation that life is squishy. We recognize it when we see it. So that general trait that everything down below is going to inherit from that. We start with those basic properties of being alive and then get more specific. As we continue down from eukaryotes, one branch has scales and another branch has fur, hair, four limbs. I didn't draw anything with anything bipedal up here, but we could add another one where the four limbs are separated, where we walk on two of them and use two of them for something different, kind of the branch that leads to us. But We inherit all of the traits of being the life form here, add a few more details, the centralized nucleus, cell specialization, really, is the big thing. Centralized nucleus, mitochondria. Then we inherit all of those details and add more stuff onto it, like has hair, makes milk. Inherit all of those and add more details, like over here in elephant, the long trunk and what it means to be an elephant. So we're adding more and more details while still inheriting everything above us in the tree. And it goes the other way too. If we need any random life form, a beagle is one. So is an E. coli. I definitely don't know any of the names of the archaea off the top of my head. Those are things that live in like the hot springs in Yellowstone, the sulfur springs in Yellowstone National Park. That are very, very different than anything in our branch of tree of life. But when we look at it, we still know it's part of nature. It's a living thing. But those have really big fancy names that I'm not even going to try to say up here. But those are all just random life form. A canine. We need any random life form, a canine is one. But that only goes one way, right? If we need any random canine, we can't use something from over here. We can't say something on the plant branch, like an oak would fill in that gap for that. And that's the three main concepts that we're going to look at over the next few days. Encapsulation. We enclose the things like a capsule. Everything we need is included there, sealed up. The entire item is enclosed, sealed up, well-defined, and ready to go. And when we need more, in case of details, we extend it further. We don't open it back up and add more there. We extend it down to another level and add the details of that next level down. So inheritance, encapsulation, inheritance going down the tree, and then polymorphism is a big word for a simple concept. Polymorphism sounds like something fancy, but really it's the ability of one tool to behave as another. So in my hand is this marker. Everybody knows what that's for. I pull the cap off and make marks on the board, and it's the standard language. You all understand those symbols. Also, if my forehead itches, I could take this marker and scratch it. So it makes a really good scratching stick. But would we ever say a scratching stick is the purpose of this marker? It just also works for that purpose. That's polymorphism. We can use one thing for more than just its intended purpose. Right over here, where I always set my laptops for class, there's not a good podium in this room. The desk is way over in a corner, so it's kind of a bad spot to point the camera at. This is a tablet charging station. Is this unlocked? So if I open this up, oh, my keys aren't labeled. One of these keys goes to this. So if I open this up, probably hard to see on the camera piece. There's 32 laptops in there, or 32 tablets in there. So really it's a giant charger. Its purpose is to charge 32 laptops at a time. But it gets used as a podium for my laptops a whole lot more often, right? It's been like 2 years since we even ran the mobile app class on campus. So we almost never use the tablets themselves. But I use this as a podium pretty much every lecture, every class I'm using this as a podium. But that still doesn't mean its purpose is going to change and we say its purpose is to be a podium. Its purpose is still a charging station. So that's what polymorphism is. It's a big fancy sounding word, but a very simple concept. A concept that comes very naturally to us, which fits with this. And that's the advantage of object-oriented programming. We get to think like a human again. There are some standard examples kind of circulate through when we go over object-oriented stuff in programming classes, simple things to visualize, geometric objects. I think you have one of those on your homework. Cars are a good model. Animals are a good model. Come on, I think it's like cycle back around to animals. But there's different simple examples that are almost standard across the board. We'll probably look at a couple different ones each time. Like in animals, it's been at least 2 semesters since I did animal, or it's been at least 2 classes since I did animals. So that seems like a good example. Maybe we'll do cars next week. Can't really remember which one I'm at in the list, but those are our examples. We'll get there in a minute. I'm just going to draw the way we would diagram our class example we're getting ready to make. So jumping ahead a little bit to kind of the end of the night and see what we're going to make. But we would draw something like this. There's some class called animal, and then we'll have a bunch of private properties and public methods that define what it means to be an animal, what our data type animal all has in common. I'm thinking for the example, everything's going to have a name and an age and maybe a weight, things that a vet would want, that would be in the vet database. But then we might want to get more specific, multiple types of animals. So we might have cat types and dog types and I don't know, monkey, something like this. We'll probably change it, and they would all be class diagrams. I just did the one, which by the way, you probably have instructors require you to draw those out fancy. There's no thought involved in drawing a class diagram, so the computer can draw that. A human is needed to organize it. It can be very, very difficult to organize that in a way that you can see all the arrows, especially if your software gets big and stuff. There's no way to put everything without some arrows going over across to others or things overlapping. So the organization is hard, but a computer can draw these all day long. So we'll look at some generator things so that after we type all our code, we just click a button and then we get all those pictures with the arrows connecting them, but they'll be in like an arbitrary form. There's one I really like where you just stacks them all up in a corner so that we have to reorganize it. A computer can draw the picture, but a computer can't organize the picture nicely. But see, just right off the bat, it's kind of following the way this tree's drawn. And these get more specific. So one type of cat might be a lion or tabby cat. That's a type of cat. The little gray ones with stripes. I guess lion could be off on its own somewhere, and not because cat seems to imply the little house cat, but it is still a cat. They have a lot in common. So we would inherit all these properties from that it means to be an animal, add a couple more, and then add more details for the specific one. Or for a dog, we can do the same ones that are over here. There's a beagle and a chihuahua. Other types of monkeys. But that's probably enough on the picture. You can see when we diagram what we're getting ready to look at in code, it matches the diagram of the way humans naturally categorize things. And that's the biggest advantage in object-oriented programming, is we get to think like a human again. I mean, there's still that adjusting your train of thought and the back and forth debugging stuff to get the computer to run each like method in particular. But in the overall picture, we're categorizing things and thinking like a human, thinking like we normal, what naturally flows out of us. Which the trade-off for that is it's bad for the machine. It is less efficient for the machine. But you've probably noticed, even if You very first programming you saw was when you came to Ivy Tech, and all you had is two prerequisites for this. Probably noticed we don't use non-object oriented languages anymore. They still exist. You might hear about them. Might hear people mention that if you go ahead and learn COBOL, there's pretty much a job guarantee because there's still legacy systems running, and maybe only a dozen people in the world that know COBOL. So those still exist. But we do pretty much everything in an object-oriented programming language, which is less efficient on the machine, which automatically runs slower. The general numbers I put up there is if the programmer can do 1,000 times more at a 10% loss in efficiency, which those are made up numbers, generic, but that's sort of the picture of what we're going for, right? The programmer can do 1,000 times more, so plus 1,000 at a 10% loss in efficiency, so minus 0.1. And overall, that math is gonna, that's not a 1, minus 0.1. Overall, that math is, it's way in the positive, right? We're not losing nearly as much as we're gaining by being able to think like a human when we look at the big picture. So that's what part of the reason it took off. It did take a while. The idea first showed up in 1962 in Norway. I'm not even going to try to pronounce the guy's name. I think it's these notes here. These notes here on the desk were being prepared before my first semester teaching here at Ivy Tech. I think I did try to write the guy's name down in there. Got 7 or 8 letters into it. It's just like, I'm just gonna say Norwegian guy. He was a Norwegian guy. You all have seen Norwegian names spelled out. I'm not even gonna try to pronounce it, but it was around 1962. Norway is a very rich monarchy, so they had the nicest computer in the world in 1962. And his idea worked great. Other programmers tried it, it worked great. But that was on like the nicest computer in the world at the time. So the rest of the world couldn't really handle it. Around 1984, 85, what we would call the average computer was finally capable of handling object-oriented programs. We could finally had enough resources, enough RAM and CPU power, and enough speed to handle that inefficiency from object-oriented categorization that we could do it on an average computer. And y'all are probably well aware of a big change in computers in the mid-'80s, right? Once we could do that, it took off. It spread like wildfire, and we hardly even do things that are not object-oriented anymore. It's everywhere. It's just so much better for the human, and the machine never complains about the extra work. So very, very popular thing, but there's a lot of advantages to it too. So even if the machine did complain, there are a lot of other advantages that outweigh the disadvantages consistently. So that's our next little topic. Okay, if I erase the pictures and get into actually talking about this. This is jumping ahead. This is what we're going to do here in a little while after some talking and diagrams on the board and all that. We might do vehicles or something tonight. There's lots of standard examples, and we're going to see a few over the next couple of days, and then you'll have a few more in your homework and a few more in your final project. So, object-oriented programming. Right off the bat, y'all already see what the anagram for that is, right? This is technology. We use anagrams everywhere. And a very, very common thing is to go ahead and throw an S on that anagram. Because now it's one of our most common words we say, right? So that fits a lot nicer in lecture. So I'm going to do that. You probably wouldn't have to think very hard about to get an S into that as well. Object-oriented programming software works. But then now for our lecture, I can just say oops instead of that great big long thing. And for those taking notes along. It's a whole lot easier to type. Spell check will actually correct, or spell check won't change things if you type oops. We're like, yeah, that's a word in English. It'll keep it in your notes. If you're writing by hand, it's obviously a lot quicker to write. So different ones you might see the just regular OOP anagram, but it is very, very common to go ahead and add that S in there. And then we have a word with it, a common word with it too. And we could probably dive deeper into the lexicon there and come up with all sorts of reasons why oops was great with programming. Kind of describes a lot of our processes. Like I said, it's more like how humans think instead of how the machines process. It provides us with reusable code that can be easily modified. So reusable code, that's like our methods. Right? We saw reusable code with methods calls. We can adjust parameters and send things in, but we're still somewhat restricted on any changes to them. So that last little bit can be easily modified to meet new needs without starting over. That picture I just erased probably would be a great place to point the stuff there. Up at the top of the tree, we start with the general one and start adding details as we go down. We don't have to go all the way to the top of the tree to make something different. We can pick one of the levels in the middle or something at the very bottom of that tree and make another level further down, or jump to the middle of the tree and step off to the side, and gives us a lot of different starting points without going back to the drawing board every time like we have to do methods. So objects have properties and behaviors which can be inherited by other objects. I'll say objects are defined by properties and behaviors that can be inherited by other objects. So we're going to talk a lot about this, and in general, you refer to business settings because businesses have the money. And we're in college to get the big paychecks, right? So we want to make sure we're in that mentality. I'll say right now, what helped make this most clear for me, really understanding, is game development. Not with the big engines, just some simple games, and start categorizing things so you can think about them in that like virtual world. Everything is becomes its own little noun separate from everything else. We can close it, and game development really helped me understand it a lot better. But this isn't a game development class. I spent a little more time on that because there wasn't any development classes. There are game development classes that seem to fill up every semester. A lot of people are interested in that. Not that that's a surprise or anything. And we also add sort of layers and protection between the properties and behaviors. So I like the donut picture. Am I still on the camera here? Yeah. So sort of layers of circles. And in the inner circle, that's where our properties are. The stuff that defines the object we're making. What color is it? Is it expensive or cheap? The size of it, and little things like that. All those details, the single data points that define it. We put those in an inner circle where they can be nicely protected by the behaviors in an outer circle. The stuff that object is capable of doing. Such as if we have a color property in here, we probably have a get color behavior that will return the color that's stored in that data field, that property. You might notice I was trying to put off the proper vocab terms, but I just slipped up and said data field. It is not a coincidence that those properties have the same name as the cells in a relational database, or the attributes in a graph-based database, or in a document-based database. We're actually using object-oriented programming directly, so that one's a bit more obvious. But it is not a coincidence that we call one of the terms for these is data fields. We use those directly. So I might as well put that up here since I just slipped up and said it. So properties. The terms we want to use for that are going to be data fields or attributes. Oops. Those are going to be the technical terms, the correct answers on multiple choice quizzes like certification exams and weekly homework assignments and stuff like that. Data fields and attributes. But when we think about it, it's a variable. What variables define this object? What color is it? How big is it? For the animal one that I had up there a moment ago, how old is the animal? What's the animal's name? How much does the animal weigh? And those individual data points that make it up. So they're in that nice little center of the circle. Protect, held private. We're going to talk about private and public and our access level to them. But it's really good form to keep them private as much as we can. But you definitely wouldn't have seen this in the prerequisites of this class, because Python does not have private data. We have that double underscore thing, which means we have to type the class name, then 2 underscores before accessing the variable, but it's still readily accessible. If we say, when we say our data fields are private in Java, the compiler will remove all access to them. So once they're listed as private, the internal to the computer, there is no access. There is no longer access to them, except from that text file, basically. So once it's compiled, there's no way to change it except by public methods. And behaviors, our technical term is going to be methods. And you'll want to watch that closely on multiple choice quizzes and certification exams, because they will try to trick you up. Functions are for procedural programming. Methods are in object-oriented programming. So for an object-oriented programming, we only have methods. We do not have functions in Java. That is a common little trick you'll see on various multiple choice questions, certification exams. So no functions out there, because when we're talking about them, we're going to say both. We use those words interchangeably, right? So we've probably already seen that a lot leading up to this class. Methods and functions are interchangeable, but technically methods are object-oriented, functions are procedural, and they're, the correct answer on any quizzes is that they are not the same. But the correct answer when you're talking to other programmers is just using whichever one fits better in the sentence you're saying. So watch the technicalities like that, because we can also say variable about our properties, our data fields, attributes, variables. But technically that would be an incorrect answer, because variables are for procedural programming, and data fields are for object-oriented programming. Which again, it is not a coincidence that we use the same term there that we do in database. When we get to the MySQL section here in 2 modules, I think, maybe 2 weeks, maybe the next module. We'll have our MySQL database off to the side, and then the things stored in those tables will be brought right into our properties. They're interchangeable. It's 2 ways of viewing the same thing, basically. That's not what I wanted to put on the picture here. That's jumping ahead and talking about the terminology. So once we have those things, get color, what else is here? There's a size, so we probably want to set our size because we need a way to change it I just said if we keep those private, there's no access to them. But the public methods, there is access to. So we just need to go through the behaviors to access the properties. A layer of protection. And then out here somewhere would be our client that asked for those. So the Java code holding our main method, the operating system starting our program, other software entirely. Wherever we're asking for that object, it has access to the methods, the behaviors, the public portions of that. And then the behaviors have access to the properties, attributes or data fields or whatever term we want to call them, whatever term we want to use for that. So I can refer to that as the donut picture to kind of summarize them nicely. And our first concept from object-oriented programming is encapsulation. The donut picture kind of shows that nicely. I'll put quotes on it because it's one of our important words. Encapsulation. And you'll notice the word capsule is right in the middle of that. That's all I like to think about. We put everything that it means to be our object together and close it up in a capsule. Kind of like a time capsule, right? We take everything, take a bunch of items that represent what it means to be alive in 2022. What are some items? I guess they're all technology items. Let's go back a couple decades. Everything that needs to be alive in, say, 1975. Like bell-bottom pants, those paisley shirts with the floral powdered paisley shirts, the big disco high heels for both men and women, all and newspapers, shag carpeting, all the stuff that it would mean to kind of define life in 1975. We put that into a box and seal it up and bury it. A time capsule, so everything's sealed up there, held there. It can't be changed once it's buried in the ground. And then somewhat later, when we need it, we just kind of open it up and take a look. So that's what we're doing here. We're putting everything, we're defining this particular thing and sealing it up in a capsule. And then when the client needs it, it just kind of takes a peek at it. It can look at what's in the box, but right, like a time capsule from 1975, that's stuff for a museum, right? We open it up and it's treated like a museum. It's held behind glass, so we can't actually touch it and damage the delicate plastic, polyester fabrics and things like that. But we can look at it and that sort of idea. So our capsules right there. We seal everything up in capsules. Important terminology that you'll see on like certification exams and stuff that goes with that is, do I have room on the board here? What's called the open close principle. One of our key concepts in encapsulation is objects are open for extension and closed for modification. So back to the capsule thing, it's sealed up, we can't modify it. But open for extension. So what I put in here? Color, expensive size. Along with color, maybe there's a sound property. It's like, whoops, I have a sound, I have some detail, I have some sound data that would include there. But our objects it's encapsulated, it's closed for modification, but it's open for extension. So we could make a little child class that gets all of those things and then adds a sound property to it as well. So we extend our classes to make modifications. So there's that reusability that is easily modified. We don't have to go back to the very beginning and rewrite the whole thing if we want to change it. We can pick it up somewhere in the middle. It's okay if I erase this and get started with the ones that are going to be our first example. Kind of syntax example. I see head nods here in the class. Everybody get a picture of that or something, or get it written in your notes. The open close principle is an important one all across computing. So you will definitely see that on certification exams and things like that about languages. Open for extension, close for modification. Our core concept in object-oriented programming, or a technical way of describing encapsulation. Almost like a definition. Let's do the animal class tonight. Animal objects. So we're good. I think everybody was required to see UML class diagrams in the previous class. Prerequisites for this, right? Square boxes. We list out our data fields with a minus sign if they're private, a plus sign if they're public, a hashtag if they're abstract. I haven't talked about abstract stuff yet. We'll see that coming up soon. We're going to be talking about objects for a while and working some finer details. I'm going to do everybody's seen those, so I'm just going to do the donut pictures, and then we'll look at the UMLs in more detail when we have all of the symbols. Which that's another one. Oh, I don't think you did in the prereq. So, UML, Unified Modeling Language. It's an international standard of communication. Right? Technologies stretch all across the world. Humans speak different languages. So we need to cross that language barrier. So we have a pictorial-based language to cross the language barrier. A standard across the world. Everybody's using the same pictures, so we can look at them and understand what's going on. Entire language, and the one for object-oriented objects looks something like this: square box, and there's a solid line, and we have our object name. Which I guess I should write class name. We have our class name up top, and then we have all our data fields. So a minus to indicate it's private. So like private string data name, a private integer data age, and so on and so forth, and list out all our stuff that way. And then a dashed line, and then we get into our methods. So a public method, I'll say get name, that's an easy one. That's going to return the value of that. So it's going to return a string. So we have all our information about it. What type of data is it? Data types, like we've been making a big deal out of for a strictly typed language, right? What are we going to call it in the text file? Some useful reference to it. Is it private or public? And there are more symbols we'll see there before long. We have inheritance, so other things can inherit all that and extend it further. Dependency. So if our object depends on another object, or our class depends on another class, we need to mark that in our diagram. So that's a dashed line. Which one's filled in there? Our aggregation and composition. And all that stuff, all the information we'll need about that. We'll talk about aggregation and composition soon. Probably next Tuesday. I don't think we'll get there by Thursday. But lots of different things in this nice official diagram, square box. Your book is full of these, right? You've seen things that look kind of like this in the book already. The way we draw our arrows makes a difference. We won't see it here, but we also have the dotted arrow. But that's not what we're going to see in the class. And all these different things have meaning with relationships between our classes and what we're doing. But we'll see that soon. Does that look familiar to everybody? And if we already wrote our object in the text file, it doesn't take any thought whatsoever to draw that picture. Right? If we wrote a whole bunch of child objects, it's not going to take any thought whatsoever to draw that arrow and connect all the child objects to it. So a computer can draw them. But when we start to get a lot, a computer cannot organize them nicely on a page. Right? A human has to organize them, but we'll just click a button and have them all generated. It's a lot easier that way. I'm still looking at the same doc there. I should open the chat room so I can see that on the screen in front of me. So that sort of picture, I'll erase these extra arrows. We will talk about those in turn. For now, I'm going to start with the little donut picture like I had up there a moment ago. So we'll start with animals. Or would cars be better? Any input? Should we do animals or vehicles? What did y'all see in the previous class? No comments? Let's do animals. We'll look at a couple over the next few days. That way we see it in different situations. But I can't remember what the SDEV 140 class has in the statewide shell right now. So I want to try to change it up from the previous one. I think they're doing cars, right? They have cars in their example. But it's been a year since I taught that class. So I've taught a lot of classes since then. So they kind of blend together. So we have our first one up here. And we need some properties about what it means to be an animal. Our general one, for our example, everything is going to have a name, an age, and a weight. And what we're really making here is data type. Over here, I kept using that word. I said we have a string type of data and an integer type of data. And those that we've looked at so far, those are primitive data types. Those are just the basic binary code. But usually, we want to represent something more interesting in our software, right? Like we want to represent an employee so we can do the payroll calculation and vacation requests and annual reviews and all of that connects to that same type of data. So we don't want to go back all the way to the primitive data every time. So we make a more complicated data type, which that's another one that those people often first is objects. They're reusable, that they don't compare to methods. Objects compare to ints and booleans. Objects compare to strings and chars or characters. It's a data type itself. It's just a more complex data type to fit our needs. Employee examples are great one because we have lots of different needs of an employee. Right? Every week there's going to be a payroll, like our example the other day. Once a year there's an annual review where there's probably a bunch of notes about that particular employee. We don't want to go back into their name and age and hire date and rate of pay and all of that every single time. Because it's, for the most part, it's the same data. It's data representing the same real world physical object. So we want a virtual version that matches that real world version so that it's kept together and closed and accurately virtualizes that real employee for a company. So objects are data types. They're just complex data types. So we'll have a couple here, name, age, and weight. Looks like a string, an integer, and floating point number. Sounds reasonable for those, right? Then we want some getters and setters. Getters and setters. Since all of those data fields are private, we need a public way to access it. So like a public get name, and a public set name in case we change it, or public set age so that we can change that. And there's some naming conventions that we stick with very tightly in Java and C# and most of our other programming languages. We stick with the modern languages. And in operating system control languages is like when Windows updated from those old ones made back in the 1970s, where we abbreviated everything to a modern scripting language. They followed those same naming conventions almost perfectly. They put a dash in them in PowerShell, and PowerShell can be ported to any operating system. So you can run any computer from PowerShell. I usually run my Kali Linux from PowerShell. Goes right on a Mac, any type of Linux system, with a lot of modern advantages that weren't even known in the 1970s, when things like command prompt or Bash was created, the precursor to Bash. But they made a few updates along the way, but they never did a complete overhaul. So it was still that 1970s style language. Our loops look weird, and our selection structures look even stranger. So PowerShell just updated to a modern language to control our operating system. And then everybody else scrapped their plans to do it. They're just like, okay, this is one of the things Microsoft did a great job at. So they just imported that. And if you go to the official documentation on Microsoft or Linux or Apple stuff, you'll see the copy and paste commands to put PowerShell onto whatever system. So we're seeing more and more of it there, and following those conventions, the modern language. We say get and set. This is another important one to write out vocabulary wise. So our technical terms, the correct answer on multiple choice quizzes or certification exams. Certification exams are multiple choice quizzes. So like those weekly quizzes you'll see in your programming class, a lot of those are going to be very, very similar to certification exams. So that's what you do. You don't get certified in Java by sitting down and writing Java code. You get certified in Java by sitting down and answering a bunch of multiple choice questions about Java. So in some sense, the weekly quizzes are more useful for the Java certification than the programming job. Obviously, it's an active subject. You're going to need to write a lot of programs to be able to answer lots of those questions correctly. But the certification exam you don't write programs to get certified on it. So getters are actually called mutators. And setters, the technical term, oh, that's backwards. Sorry, setters are mutators. It changes it. We change the value, we mutate that value. And getters are accessors. So we access the value or we mutate the value. Is the technical correct answer when you're taking multiple choice quizzes like weekly homework assignments and certification exams and all that. But anytime you talk about it, including the buttons on pretty much IDEs, when you go ahead and just generate that code instead of typing it yourself, it's going to say getters and setters, because that's normal English version of what we're doing. We're getting the value, or we're setting the value. That one, there's a big discrepancy in how we talk and what the technical correct answer is. There's almost never overlap. Nobody uses accessors and mutators in sentences. Those are just too fancy of words. But then we might have some other methods. Any of our animals are going to make a sound, right? So that'll be our main method. Make sound. And along with that, we're going to do this in Java. So there's also another object way up here. sort of a grandfather object of everything that we implicitly inherit from. There's this thing called object, which is a master class that everything inherits from. It has a two-string method and an equals method. It defines what equality means. And those two we almost always want to override. Because the default is, if you say to just print it, the default that everything inherits implicitly from that master object, the grandfather level object, using parent-child terminology, the ancestor of all our objects. The default two-string is to tell you which spot in RAM it is. Not very helpful for a unit. The default for equality is that they are stored in the same location in RAM. Which sounds like it wouldn't be as useful as it is. Java has really excellent memory management that goes on in the background. We're not dealing with C++, we don't have to handle that ourselves. Java has some of the best garbage collection in the world as far as programming languages go. So it cleans up memory constantly, and if it notices that we stored 3 in 2 separate data fields, it's going to delete one of them and point them both at the same thing. But there's no need to store this twice. So it will automatically do that. So the only time it would miss it is if you're in the few milliseconds between the next round of garbage collection. So you have a few millisecond window there where it might miss 2 3s being equal, but it's usually going to catch it. It's going to clean up memory very soon. So we inherit a few things there. There's also a hashing algorithm, so we can put things in hash tables. We'll talk about hash table later in the semester. It's a very important one for how the computer works. So if we interact with it directly, we get way more speed. And other things, efficiency, but speed's the one we care about, right? And like, well, they're machines. The typical souped up car usually has lots of nice features, right? A typical souped up hot rod is going to have fancy paint jobs. It's going to have probably really great suspension systems. But people aren't going to talk about the great suspension system of the hot rod. They're going to talk about that fancy engine that makes it go really fast. That's the one we care about, even in computers. There's lots of things there, but we care about the speed, which is probably going to increase a lot today. Before we take a break, did anybody watch the Nvidia annual conference today? The keynote was today. You should definitely check it out. There were some really interesting things. We'll talk about that some maybe break or as we wind down today. But a lot of their future plans, it's Nvidia, so obviously GPUs are there. And they also included a workshop on optimizing GPU, because there's some things that have always been a problem when we go to put our programs on GPU, especially parallel stuff on across GPU. And Nvidia actually made it a point to sit down and teach people how to get around that. But it's high level programming. It was complicated to watch that. It's like, wow, I had to keep pausing the video and thinking really hard. It's like, okay, somebody will probably simplify that soon. So it's nice to get around one of the biggest problems with programming, splitting up things parallel across the GPU. Because, well, the problem is GPUs tend to tell us they're busy when they're not. Like, yeah, running at 90% capacity. It's like, okay, how much is that useful? GPUs are like, oh, well, there's 8 bits that are actually going to be used. GPUs are really bad about that. So we lose a lot of efficiency there. But that's a much later thing, kind of a sidetrack. Really interesting things. And DPUs are in pretty much all of the future plans Nvidia announced today. Data processing units. So I was really excited about that, because now we have the CPU, the GPU, and the DPU to specialize our processing and really work do things. Like a big deal, like data processors for like a desktop tower. And Nvidia's new one is a chip. It sits right in there on the motherboard with the other stuff. I was excited about that. That's the one that got me on the sidetrack. Sorry, back to object-oriented stuff. Interesting technology advances on my mind. We're working on we got to build our base foundation before we get to that. I will share the link with y'all before we leave tonight, though, because the keynote was definitely worth watching. So that gives us what it means to be an animal. as far as like the vet's concerned, there's probably other stuff there. But our simple example, syntax. The simple syntax example, we're gonna say the vet needs to know every animal's name, its age, and its weight. And then there might be some other details that we want. Different types of animals. So for example, one type of animal might be a lion. And here, unlike that earlier picture, I'm going to separate lions and cats. Well, actually, I could do feline. Now, for our example, I'll keep it simple. I could probably put a bubble in there that has the balance issues, the legs further towards the corners of the animals than they would be on a canine. So they have more optimal control and balance, all those things we see with a cat. And that would include lions and dogs. But for this example, I think I'll kind of split it up this way. And all of those are going to inherit those properties. But there might be some problems when we do a generic animal sound that'll apply to everything. Maybe a gorilla too. That sounds like a good example. Well, we probably want to put something in that sound. There's a method there. That method needs to return something. So we'll probably set a default value. Say return roar. That sounds like a good generic animal sound, right? We can return a roaring sound, and that'll cover almost all our animals. That's gonna work fine for our lion and gorilla. They can just inherit directly from that. We fill in the name, age, weight properties, good to go on those. But roar doesn't quite sound right for the cat and the dog. So we'll probably want to override those methods. Make the cat circle a little bit bigger here. So for our cat object, we'll override the make sound method. I'll just write it in here again. We'll change that default one. Override is like the most misused word in Hollywood. I guess I think it sounds fancy. Yeah, next time you're watching a movie and you see the characters say, in order to save the day at the end of the movie or TV show or whatever, you hear the character say they're going to override something. Imagine that character saying, I'm going to try changing the default value. So that's what override means. Override means change the default value. It's really ridiculous in the situations they put that in Hollywood, but just picture the character saying that next time you see it in a movie. It kind of becomes a little bit comical. So for our cat, instead of returning the roar, we'll return meow. Likewise on the dog, we'll just override that make sound method. So we'll change the default value to return, I guess, woof. Sounds like a good dog sound. Fill that in our bubble. Then we can do more detailed examples under that. So like specific dog types, like black lab or chihuahua. But I think our first syntax example isn't going to be that specific, and you can see where it kind of goes from there. And then those things that I said we might want to override. We probably want to have some selection structure somewhere, right? So we need to know what it means for our object to be equal to another object. I'm going to put that, I'll write an OR next to all these that I'm overriding. So we want to override equals and redefine what it means for our animal to be equal to another animal. What would be a good way to say that? By type, by age. Two animals are the same, we'll call them equal. A 12-year-old cat, a 12-year-old dog, to the vet's office, 12-year-old pets, the weight, right? We're going to just categorize everything by how much it weighs. Think about that. We'll pipe it up after the break, and I'm going to ask for feedback on what you all think is the best way to define what it means for two animals to be equal. And I guess it's going to be a very generic syntax example, but maybe think of a vet helps. What would be most useful for that vet to consider two animals equal? So we can run selection structures. Comparison will need interfaces, so we won't see that till next week. Comparisons we'll get to when we get to the interfaces. Oh, I also want to override the toString method, which that is what automatically gets called if we say print our, if we say system.out.println and just pass in the reference to our object, it'll call the toString method. So that's something we're going to want to do. Even later when we get to fancy outputs, a JSP page where you put it in HTML, that's where the toString method is going to go. In that case, you might want some HTML tags in there, make it look nice or something. But what does it mean when we print our object? When we print this data type? Stretching out the explanation on this so that hopefully y'all have time to think about different things, situations you've seen before, things you would do different than what I drew on the board here. I'm hoping you have some of those ideas, because if I'm making some notes on the board and you just completely disagree with the way I did it, that is a great sign about being able to program, right? Because obviously we're unique individuals and we're going to think differently. So we would all, there's those little details that we would all do differently. So hopefully you are seeing some things that you would do differently. Okay, I think we're ready to type up our syntax, see this in action, but it's probably a good time for a break, right? It's been a few minutes. 10 minutes sound good? I see head nods in here. Any comment from the Zoom call? See thumbs up? All right, so it's 7:07 on my laptop, so we'll get back to it at 7:17 and type this up in Java and see our syntax, but y'all can probably already guess at a bunch of it because we had to make objects to do our main method. But I will see y'all in a few minutes. Oh, stop button's over on this one. Stop recording.